Good afternoon to all of you once again. So, in our ongoing discussion of various strategies relating to divide and conquer, we'll be exploring some of the algorithms that involve the divide and conquer strategy. That is, these algorithms apply the divide and conquer process to simplify a larger problem, then recursively solve each of these smaller sub problems until they get the final outcome. So let us just check out the definition of merge sort algorithm. It states that it is an efficient, stable, comparison based divide and conquer sorting algorithm. So it's an efficient algorithm because it divides a larger problem into smaller sub problems, and it's stable also, and comparison based because we are comparing. When we are dividing a large problem into smaller sub problems, we are comparing them and solving them recursively. Okay. Used for sorting data in many systems due to its predictable performance. Because it has a complexity of n log n, which is very efficient, it is used for sorting data in larger systems, because it, no matter how large or how varied the data set will be, the complexity will always be n log n. So what does it actually do? So it divides the array into two halves, sorts them, and then merges them back. Okay, so it will divide the array, it will go on dividing the array until, so in case of merge sort, it will continue the process of subdivision until and unless only one element is left. When one element is left, it will stop the divide phase and it will start the conquer phase and start to merge the results. So it uses the divide and conquer strategy to achieve proper sorting. So what are the steps? These are the basic steps. I will be showing you a simplified algorithm later on. So it is division of the array. So first step involves splitting, that is subdividing a larger array into two halves. So as I have said to you before, this division will not continue forever, but it will stop when there is only one element left in each of the divided pieces. So once the division phase is completed, it will start the conquer phase, in which it will recursively sort both halves and combine them. So after the conquer phase is over, the combination, that is combining of each of the sorted halves will take place, and finally after combining the results repeatedly, you will get a single sorted array. The sorting may be done in ascending or descending order, depending on what you want to do. So let us see a visual example. So in the first step, you can see that there is a array of size 1, 2, 3, 4, 5, 6, 7 elements. So there are 7 elements on the array. So here you can see, so the indexes of these elements are from 0 to 6. So when you are dividing it into two halves, so here the mid position is 3. So we are dividing the array at the third index. So so the first half has 3 numbers and the second half has 4 numbers. So in the first half, what we've got 38, 27, 43, and in the second half we have 3, 9, 82 and 10. So as I have said to you before, the division will not stop until one element is left in each of the halves. So in the first half there was initially 3 elements, so we are again subdividing it. So when you are dividing an array of 3 elements, okay, so the midpoint will be the so 0 plus 3 by 2, that means the 1 will be the midpoint. So when you are dividing, 0 plus 2 by 2, that means 1 will be the midpoint, and 38 is 1/2, and the remaining 2 elements constitutes the second half. So 38 cannot be divided further, but the array having 27 and 43 will be divided once again, which we'll see in the next slide. So now in the second half, so in the previous slide you can see there was a second half having 3, 9, 82 and 10. So here we divide this half into 2 more halves involving 2 numbers each, that is 3, 9 and 82 and 10. So now 27 and 43 will be divided, right? So after dividing, okay, so 27 and 43, you can see that they are already sorted, so there is no need to sort them any further. So now while you are merging the result, you will have to insert 38, which was a part of this group, into the appropriate position. So 38 lies between 27 and 43, so it is inserted there. So 3, 9 will again, it is subdivided and it is combined. So 3 and 9, when you are dividing them into 1 element each and then you are combining them, you can see that it is already in sorted form, that is in ascending order. So there is no need to sort it any further because it is already sorted. Next comes 82 and 10. So 82 and 10 were the part of the second half, right? So 3, 9 we have already combined, and now we are sorting and merging 82 and 10. So if we are sorting between 82 and 10, obviously 10 is the smaller value, it comes first and then 82. So now when we have sorted these 2 halves, that is 39 and 3 and 9 and 10 and 82, 3 and 9 and 10 and 82 are already sorted. Now we are going to combine them into a single large piece which involves all the 4 numbers. So here you can see that the numbers are already sorted. So the first half where there was 27, 38 and 43 sorted. The second half where there was 39, 10, 3, 9, 10 and 82, that is also sorted. So here we are going to combine the result into a single large array. So when we are combining the results, we are going to make sure that all the numbers are in sorted order. So here you can see the results are sorted. So this is the problem solving approach which uses merge sort. So first we are going to divide the array into smaller pieces, then we are going to sort them if required. If the results are already sorted, then sorting won't be required, but if it is unsorted, then we'll have to sort them, and then we are going to combine the divided pieces, that is merge each of the divided pieces together until we get a single large array. So this is the simplified merge sort algorithm. So it says if the array has 1 or 0 elements, it is already sorted. So we are going to return it, because if there are no elements or if there is just one element, it is not possible to sort the array. So we are going to return the array as it is. But if it has at least 2 or more elements, then we will divide the array into 2 halves, then recursively sort each half. Okay. So after dividing the array into 2 halves, we are going to sort each of the halves and then merge the 2 sorted halves into a single sorted array, as I have demonstrated earlier. Then once the each of the halves are combined into a single sorted array, you can return it, because sorting is completed and whatever we had set out to do, we have achieved it, right? So here also we are seeing another explanation. So let us see, we've got an array consisting of 8 numbers. So here you can see the numbers are scattered throughout the array in a randomized fashion, so neither it is in ascending order nor descending order. So now while we are dividing the array, we will continue the process of division until and unless in each half there is just one element left. Okay. So from 8 and 3 you are getting 8, 3, 2 numbers. From 5 and 4 you are getting 5, 4, 2 numbers. 7, 6 getting 2 numbers, and finally 1 and 2. So after this we are going to sort the array. So we are from 8 and 3 we are sorting them, and then we are going to merge them. So as we are sorting them in ascending order, you can see from 8 and 3 we have got a sorted pair, that is 3, 8, and so on and on until and unless all the pairs are sorted. So after that we are merging 4 and 5, then 6 and 7, and 1 and 2. Finally each of these pairs comprising of 2 numbers are merged once again, and we get 2 partially sorted lists, that is 3, 4, 5, 8 and 1, 2, 6, 7. And finally from these 2 lists we are getting a final array which is sorted, which is completely sorted. So what are the advantages of merge sort? It is a predictable n log n time complexity. While dividing the array into smaller halves, it takes log n, and during the combine phase, to combine each of these halves, we take on time. So for combining n halves we require n into log n time total. So whatever the size of the problem, that is size of your input, whatever the size of the array may be, which is the input to the merge sort algorithm, you will, on an average, you will get n log n time complexity always. So this is very useful, and the complexity can be predicted because of this. So it is stable. Okay, so when stable sorting means when you are sorting something, if the sorting process disturbs the original order of the elements, okay, so it is said to be an unstable algorithm. But elements, here you can see that stable, as it is a stable process, the original order of the elements, equal elements, is preserved. Okay, so it is a stable algorithm, and it is used for sorting linked lists and large data sets. What are the disadvantages? Requires additional memory space. Obviously, if you are dividing a large problem into smaller fractions, you will need a lot of space in the memory to store each of these fractions. So it is not ideally suited for situations where memory space is not in abundance. If you are having a situation where memory space is constrained, is severely constrained, then this may not be a good way to solve that problem. And it is not ideal for solving problems where smaller data sets are involved. For those situations you can use a simpler algorithm like, say, insertion sort, bubble sort, and so on. Complexity best case is n log n, average case is also n log n, and worst case is also n log n. So space complexity is on. So space complexity is not that much important for us. What we need to understand is the time complexity. So log n for dividing the array into smaller halves, and n on for combining each of these halves into a single sorted array. So total it will be on into log n. So in conclusion, we can say that it is a powerful and reliable sorting algorithm, and it is ideal for situations where stable sorting is required. Okay, stable means the original order of the elements will be preserved, and memory is, it is not limited by memory space. When the memory space is available in abundant quantities, you can apply this algorithm. So this is the end of this video, and I'll see you in my next video.